Hello all, welcome back. Today we will be continuing with our previous topic from the subject aerospace propulsion. So previously what we have studied is basically the different type of propellant pressurization systems as well as the type of effects that in case of absence of the pressurization system, what are the effects that can be found. Now continuing the same topic, we will be going for the factors that are influencing for selection of the required mass of the pressurizing gas. And a key task, that is the analysis as well as the design of the tank pressurization system, is determining the required amount of the pressurizing gas. What is the amount of gas that is required, right? And there are many factors though that influence this requirement of the mass, as well as some of them are bit intricate to understand and to digest. The gaseous mass that may be estimated using the simplifying assumptions, but it is always more than accurate when based on the actual test results that are to be performed or compared from the data that is being collected from similar proven pressurizing systems. The following that we will be discussing are few influencing factors that should be accounted for. The first one is nothing but the evaporation of the propellant, and at the interface between the pressurizing gas as well as the liquid propellant is a key phenomenon. What do you mean by that? Basically, in a tank, right, in any liquid propellant tank, we will be filling completely, right? It contains some amount of the propellant, liquid propellant itself will tend to evaporate, right? Evaporate either due to the condensing nature or due to the temperatures at which it is being kept, right? Particularly the ambient temperatures. So based on this, what happens? The propellant tends to evaporate. As the propellant evaporates, and there will be a small interaction from the pressurizing liquid to maintain the opposite force to pressurize the complete propellant. Now, what is the interaction, right? The common interface between them, and what is the interaction with respect to the type of propellant as well as the type of pressurizing gas that has been selected. The evaporated propellant dilutes the gas, and that changes the expansion properties of the gas, right? As well as this change depends on the temperature difference between the gas as well as the liquid. Now, as there is small cavity available within the tank, particularly the propellant tank, sloshing as well as the vapor pressure of the propellant and turbulence and local gas impingement velocities will differ, right? And based on this, a completely new properties, right? The properties of the gas may change. Next one would be the temperature at which those propellant tank walls, which form a part of the exterior vehicle surface, are exposed to the atmosphere and are affected by the aerodynamic heating. What do you mean by aerodynamic heating? Earlier, what we have discussed, basically any tank that we have selected will be aligned to maintain the rocket structure, either the tandem points or the concentric tanks, anything, right? They are made as spherical, semi-cylindrical with spherical ends to maintain the cylindricity of the rocket and to maintain the aerodynamic effect, right? To maintain the aerodynamicity of the vehicle. So with that part, what happens? As the rocket tends to move farther from the ground, it tends to heat up, right? It tends to heat up due to the surface friction of the air, and that tends to heat up the surface of the rocket vehicle. Now, as the surface gets heated up, the tanks that are directly in contact with the surface also tend to heat up, right? So due to the temperature that the propellant tank walls particularly are exposed to atmosphere or the ambient temperatures that are varying during the flight, and such heating effect will increase the overall gas temperature, particularly the liquid propellant as well as the pressurizing gas, and that controls or enhances the rate at which the liquid propellant or the gas tends to expand. In the other case, evaporate. Next one would be the solubility of the gas. The solubility of the gas, particularly the pressurizing gas in the liquid propellant, is affected by temperature as well as pressure. For a simple example, nitrogen gas is soluble in liquid oxygen, whereas it requires approximately 4 times as much as nitrogen gas to pressurize the liquid oxygen as an equivalent volume of water. This dilutes the oxygen, particularly the liquid oxygen, and causes a small performance loss because nitrogen tends to burn at higher temperature compared to your oxygen. But if you are using helium in case of the nitrogen, which is a preferred gas because it is least soluble in case of liquid oxygen. Next, we will be going for the condensation. What is the condensation? Condensation of certain gaseous species can dilute the propellant. For example, in a complete gas tank, my propellant, gas, particularly the pressurizing gas. Now what happens as the temperature fluctuation do occur in a tank? Due to this fluctuation in the temperature, if the gas is much more reactive with respect to temperature, as the temperature drops, the gas tends to condense, right? And this condensation will lead to form the vapor for the particular propellant. Now that has to be avoided. Next one will be the changes under gas temperature may take place during operation, that is during the flight. But the compressed gases that are undergoing under adiabatic expansion can cause a noticeable gas cooling. Temperatures as low as 160 to 200 Kelvin or minus 228 to 100 degrees Fahrenheit have been recorded with helium. A cold gas will absorb the heat from the propellant and the engine hardware. The particular nature of expansion process will depend largely upon the time and the type of propellants that we are selecting for any rocket operation. Next one will be the chemical reactions. Right? The chemical reactions particularly in some species of pressurizing gas with liquid propellant have occurred, particularly can generate heat or increase the pressure. Inert gases such as helium undergo no chemical reactions with the propellants. Turbulence, impingement, and any other irregular flow distributions of the entering gas will increase heat transfer between the liquid as well as the gas. Depending on the temperature difference, it can cause an additional heating or cooling effect on top of your liquid layers. Vigorous sloshing can also change the gas temperature. In some experimental flights of the Bomark missile, side acceleration induced sloshing, which caused a sudden cooling of warm tank pressurizing gas and resulted in a sudden reduction of tank pressure and propellant flow. In many rocket engines, a portion of the pressurizing gas is also used for other purposes rather than the tank pressurization. That is, for actuation of valves or controls, the amount that has been required once determined must be added to the total gas mass that are kept under spherical high pressure tanks, and the same mass has to be added. Now, coming to your next topic, that is the turbopump feed systems as well as the engine cycles. What do you mean by turbopump feed system? Or let us understand what do you mean by your principal components. The principal components of a rocket engine is one of the type of the turbopump system where the propellants are pressurized by means of separate pumps, either individual pumps or a combined pump, which in turn are driven by one or more turbines, and these turbines derive the power from the expansion of high enthalpy gases, particularly your liquid fuel plus oxidizer. Now, the turbopump is a high precision, accurately balanced piece of high shaft speed, particularly high RPM, rotating machinery. It consists of usually one or two centrifugal pumps and a turbine. Its high speed, high load bearing support the shaft on which the pump impellers and turbine discs are mounted. It has shaft seals to prevent propellant leakage and also to prevent two propellants from mixing with each other inside the turbopump. Some turbopumps also have a gear transmission which allows you for the pumps or a turbine to rotate it differently and usually more efficient than your shaft speeds. Starting a turbopump feed systems usually takes than the pressurized feed systems because they are supposed to build up the RPM that is required to accelerate to operate at the certain shaft speeds. The engines with turbopumps are preferred for the booster as well as the sustainer stages for space launch vehicles as well as the long range missiles, and in past also for aircraft performance augmentation. These feed systems includes the tanks in which the propellants are stored, which are usually lighter than other types such as high thrust for long duration applications. The inert hardware mass of the rocket engine without the tanks is essentially the independent of the duration. The turbopump feed systems are usually preferred when the engine has relatively high total impulse, which usually means high thrust or a very long cumulative firing duration. Pressurized feed systems are best for the rocket engines which have relatively low impulse, whereas low thrust or has many multiple amount of starts. All the liquid propellants with the turbopump feed system operate on one of the several cycles, and the three most common are shown in figure that we will be discussing in the next, which have flown for many times. The engine cycle for turbopump fed systems consists of a specific propellant flow paths through the major engine components, particularly the valves, the turbines, the pumps, as well as any other additional component that might require, and a method for providing the hot gas to one or the more turbines, and a third is a method of handling those turbine exhaust gases that are expelled out after use. And there are two types of operating cycles, particularly open as well as closed. Now, these are the three simplified diagrams that are a common engine cycles for any liquid propellant rocket system. First one will be my gas generator cycle, stage combustion cycle, as well as the expander cycle. Right? First, let us understand what are the components first. First one, we will be having the pumps, individual pumps for fuel as well as the oxidizer. Next one will be a turbine, individual turbines, and your nozzle. Right? All these are common components in all the other two cycles also. Now, what is the difference is on a gas generator cycle, you will be having an additional combustion chamber or a gas generator chamber where some part of your actual fuel and oxidizer are taken out and combusted in your gas generator chamber. Now, what it does, as a particularly fuel as well as oxidizer, small amounts of fuel and oxidizer just combined, it tends to give out the huge amount of high enthalpy gases that are again redirected towards the turbine. Right? Now, these gases are sent back again towards the nozzle, or based on the pressure ratios, we can directly leave it out towards the atmosphere. Now, if you are going to the cycle form, what happens? We can see from the fuel pump, what happens? First thing, the fuel that is either being storing under cryogenic or non-cryogenic conditions, either fuel or oxidizer is being sent directly towards the nozzle. Right? Now, what is this kind of spiral form? Is nothing but my cooling jacket. As we know, more amount of thrust what we are getting, in order to withstand the material's melting temperature, we push the fluid, particularly liquid hydrogen in case of fuel, or liquid oxygen, to cool down the nozzle as well as the combustion chamber to maintain the material's temperature. Right? So what happens? Your particularly cryogenic your cryogenic fuels which are stored under your below zero temperatures are sent through a series of passages or series of channels along the nozzle width or the nozzle length to finally give out your actual or to absorb the heat that is being generated from the nozzle and expand as it flows further, right? Upon expansion, the same gas will be used to either to drive the turbine or to directly send into the combustion chamber, right? Or sometimes the same gas can also be considered for into the gas generator for burning. Now coming to your next will be my expander cycle. What happens in the expander cycle? Basically, the fuel pump. From the fuel pump, it is directly pushed onto my nozzle. Under nozzle, as it goes on cools on, the expanded fuel, right? The expanded fuel is sent back again to my turbines, right? As the turbines run, they run my pump, and the same expanded fuel or the fuel that has been used for the turbine is again sent back to the combustion chamber for combustion, whereas the oxidizer is directly taken from my pump or the propellant tank to directly towards the nozzle for the combustion. Now what happens under this? In this we are expanding, right? We are expanding the fuel from its cryogenic temperatures to your actual burning temperatures along the length of the nozzle, absorbing the heat, and we are slightly utilizing its potential to run the turbines and to use it back for your combustion. Now coming to your stage combustion cycle. In this, it's a combination of these two, particularly your expander as well as my gas generator cycle, where from the fuel pump upon expanding, we will be sending back directly to your pre-burner, right? Pre-burner. And the same from your oxidizer pump, we will be having some kick pump, particularly to step up the pressure and send it back to your pre-burner. Now what does a pre-burner do? Basically, it burns. It burns a mixture of fuel as well as oxidizer, similar to your gas generator in case of gas generator cycle. Now, as the gases are formed, the same gases are sent back to the turbine to run the pumps that are deriving them. Now, as these are run, the same expanded gases are again sent back to the combustion chamber to burn in addition. Let's say during pre-burner, if you are having out some amount of oxygen in it, you can clear out the same oxygen and the same excess amount of fuel in the complete nozzle during the actual central combustion, whereas additional oxygen is being sent through your separate line directly towards the combustion chamber. Now, what is my open circle? As we have discussed earlier, it denotes that the working fluid that is coming from the turbine is discharged into the nozzle exit section of the thrust chamber at a location in the expanding section that is far downstream of the nozzle throat or is discharged overboard, usually that have been expanded in a separate nozzle of its own. In closed cycles, or also called as the topping cycles, all the working fluid from the turbine is re-injected into the rocket engine's combustion chamber to use it more efficiently of its remaining energy that is any available. The turbine exhaust gas is fed into the injector of the thrust chamber and is expanded through the full pressure ratio of the main thrust chamber nozzle, thus giving us somewhat a higher performance than the open cycles, where exhaust gases expand only through a relatively small pressure ratio. Arrangements where the fuel as well as the oxidizer pump are driven by the same turbine are also common because sometimes such schemes reduce the hardware mass, volume as well as the cost. The best cycle among these is whenever we are selecting should be on the basis of the mission that we plan for and the suitability with respect to the existing engines and the criteria established for each and particular vehicle. There is an optimum chamber pressure and an optimum mixture ratio for each application and for each engine cycle, both of which depend in a part on the optimization factors, so considering the maximum range and the lowest cost as well as the highest payload carrying capacity. The gas generator cycle is the most commonly used, where compared to other engine cycles, its rockets are relatively simple, pressures are usually lower, and generally they have a lower inert mass and an engine cost. However, its performance in terms of the specific impulse is less by a few percentage points rather than other two cycles. Such performance is nevertheless adequate for many spaceflight as well as the military missions. What happens in a gas generator cycle? The turbine inlet gas that comes from a separate gas generator, whose propellants can be supplied from two separate pressurized propellant tanks, can be drawn off from a main propellant pump discharges. And some early engines also use a separate monopropellant for creating the generator gas that is required to drive the turbine. The German V2 missile engine is used hydrogen peroxide decomposed by a catalyst. Typically, the turbine exhausts are discharged overboard through one or two separate uncooled ducts or a small area ratio nozzles at a relatively low specific impulse. Alternatively, this turbine exhaust can be aspirated into the main flow through the multiple openings in the diverging section of the nozzle. This turbine exhaust gas then can protect the diverging walls near the nozzle exit and the high temperatures. Both the methods can only provide the small amounts of additional thrust, and the gas generator mixture ratio is usually fuel rich, so that the gas temperatures are low enough, typically in the range of 900 to 1350 Kelvin, to allow the use of uncooled turbine blades and cooled nozzle exit segments. Whereas the expander cycle and the stage combustion cycle are closed cycles, and any small improvement they offer to make a substantial difference in payloads for flight missions as well as high mission velocities. Alternatively, they allow somewhat smaller flight vehicles. However, these engines are usually more complex, heavier, and somewhat expensive. The flow diagram for expander cycle has been discussed in the next slide, and the preferred fuel for this cycle is the cryogenic hydrogen, and it is evaporated, heated, and then fed to the low pressure ratio turbines after having passed through the engine cooling jackets. As a part of coolant, perhaps 5 to 15% bypasses the turbine and rejoins the turbine exhaust flow before the entire coolant flow is sent to the injector or to the engine combustion chamber. This figure shows you a schematic diagram of RL-10B2 upper stage rocket engine, which is an example for your expander engine cycle, where a liquid hydrogen, that is my fuel, and a liquid oxygen, that is my oxidizer, are sent to the pump, particularly through a propellant shut-off valves in case of emergencies. Now, what does this pump do? These pumps run on the turbine, and from the pump, we will be taking small amount of fuel and we will be directing it through the cooling jacket of the nozzle. Right? As the combustion takes place from the cooling jacket, it tends to take out, right? It tends to carry out the heat that is being generated in the nozzle, right? As the liquid hydrogen that is under cryogenic temperatures do absorb the temperature, it tends to expand, increasing its volume. Now the same volume or expanded gas is sent through the turbine for running your pumps, particularly the oxygen or the fuel pump. Now, as in case in this figure, it's shown as for only one turbine. In case if you are having another turbine, that will be placed along here. So the same gas would be passed on to two separate turbines to run the individual pump. In case only one turbine, we will be using a gear transmission to control or to transmit the power from one of the pumps to other pumps. Now, what happens during this? As the turbine, a small expansion of the liquid hydrogen do occur in the turbine, the gas with any other additional fuel as on and when required is sent towards the combustion chamber, right? In the combustion chamber, the oxidizer is directly added through your main control valve in the certain amount of ratios that, or the mixture ratios that are optimized and burnt effectively. Advantages of the gas expander cycle include good specific impulse and there is no gas generator available. And with a relatively low mass, engine mass, in expander cycle, all the propellants are fully burned in the engine combustion chamber and efficiently expanded in the exhaust nozzle of the thrust chamber. The turbine drives a single stage liquid oxygen pump through a gear case and a direct drive for two-stage liquid hydrogen pump. Cooling down of the hardware to cryogenic temperatures is accomplished by flowing, that is prior to the engine start, the cold propellant through the engine by opening the cool down valves. Right? What do they do? Basically, till here, everything will be under cryogenics, right? Inside the tank or near to the tank. What about this? As soon as the temperature drops drastically, they tend to condense. So in order to avoid those particular type of condensation, what we'll do? We try to push the liquid hydrogen or flush the liquid hydrogen through channel that it's supposed to flow priorly, so before the starting, so that any mishap can be averted. Now thrust is regulated by controlling the flow of hydrogen to the gas turbine and bypassing the turbine to maintain the constant chamber pressure. And a helium is used as a power boost, activating several larger valves that are operated through a solenoid operated pilot valves. Whereas in staged combustion cycles, what happens? The coolant flow path through the coolant jacket is same as of the expander cycle, but a pre-burner, right, that is a high pressure gas generator, burns all the fuel with the part of oxidizer to provide a high enthalpy gas to the turbines. The total turbine exhaust gas flow is then injected into the main combustion chamber where it burns with the remaining oxidizer. This cycle lends itself to a high chamber pressure operations that permit a relatively small thrust chamber size. Extra pressure drop in the pre-burner and turbines causes the pump discharge pressures of the both fuel as well as the oxidizer to be higher than of the open cycles, requiring heavier and more complex pumps, turbines as well as the piping. So the turbine flows can be relatively high and the turbine pressure drops low when compared to the other cycles. The staged combustion cycle gives high specific impulse, but the engines that we'll be using for staged combustion cycles are a bit more complex as well as massive. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.